Hello guys, this is Paul McWhorter from TopTechBoy.com, and we are here today with lesson number 2 in our new, improved, exciting series of tutorials on the Arduino microcontroller. And if you tuned into lesson 1, you already wrote your first few programs where we wrote a program that will make this LED blink. And so what I want to do in today's lesson is I really want to go in and talk about how an LED works, because in this series of lessons, I want us to start sort of looking under the hood and not think about computer chips or microcontrollers or things like the Arduino as just something that we type commands into. I want us to pull open that hood and start understanding how these devices actually work. And so today we're going to start by understanding how an LED works. Now, if you are following along with this series, you need to have your eLego Super Starter Kit, and link below in the description. And if you get one of these, $35, you can follow along in this entire series of tutorials. But if you already have this and look in your most excellent Super Starter Kit, you will find this little envelope of interesting things. And these are LEDs. Let me get out of your way. And you can see that you have this packet of LEDs. And we are going to be doing all types of interesting and exciting projects based on those LEDs. But today we are actually going to learn how an LED works. And so let's jump in and do that. So first of all, what I always like to do when I teach is I like to kind of go back to something you understand or something you're familiar with. And so what we'll talk about is the kind of simplest thing that you might know of how light works, a light bulb. The light bulb was invented by Thomas Edison in 1879, and a light bulb basically works like this. You have a socket. That socket has a wire. The wire comes up like this, goes back down, and then this whole thing is in a piece of glass. Now, what happens? If I apply a voltage, I get a little bit of current to flow. Current is represented by the letter I. Current flows. If I apply more voltage, I get more current. And as I continue to turn up the voltage, this begins to get really, really hot because it's a resistor, and that current going through that wire starts generating heat. As you turn it up more, it not only is hot, but it gets red hot. Okay, it gets red hot. And as it gets red hot, you can begin to see light come off of it, and it's kind of like red light, but you get a little light coming up. You turn the voltage up even more, and it turns white hot. And as it turns white hot, you start getting a lot of light off of it. That is how a light bulb works. It's basically taking a wire and heating it up to the point that it gets white hot. What is the problem with this? Well, the problem with the light bulb is that at its fundamental core, it is not a light generating device, it is a heat generating device. And if you let it generate enough heat, you will get a little bit of light out of it. But what is the problem? As you put energy in, and remember, energy is money, as you put energy in, about 95% of it goes to generating heat, and 5% goes to generating light. So you're paying a lot of money to heat your room up. So most of the money that goes in energy that goes into the light bulb goes into heat, not light. Very, very inefficient. Second thing is, all that heat accumulates in your room. Like, let's say I'm making a video here and I have lights on. All these lights start heating up the room. That means I have to turn the air conditioner on. The air conditioner works harder. It's working harder. That means the air conditioner will wear out and break quicker, and I'm having to pump a lot more electricity into the air conditioner to get it to take away the heat that was generated by the light bulb. So the light bulb's been used for the last 140 years, but it has wasted an incredible amount of electricity in generating heat, and then even more wasted electricity in trying to deal with that heat. So we need a better system to generate light, and that better system is the LED. Now, I'm going to explain how an LED works. but I have to sort of explain some solid state physics. I'll do it in a way that you can understand. It's not going to be a lot of math, but you'll develop an intuitive understanding about how these LEDs work. But to do it, we have to understand about a magical material called a semiconductor material. And again, to understand semiconductors, I need to start and explain something that you understand. So before we talk about semiconductors, let's talk about conductors. What's the simplest conductor? A wire, like a copper wire, conducts electricity. What's around the outside of the wire, like a rubber or plastic layer? That is an insulator, does not conduct electricity. So you can think about conductors, wires, insulators, plastic or rubber. Okay, the semiconductor is sort of intuitively, you could think of it as being between a conductor and an insulator, so something that would not be a good conductor and would not be a good insulator. And if you did that, that's kind of right, but the magic of semiconductors is much more than it just being material properties between a conductor and a insulator. The magic of the semiconductor is based on the manufacturing technique. You can manufacture it to be a very good conductor, or you can manufacture it to be a very good insulator. So it is a material that you can tailor the properties of. And even more magical than that is you can manufacture it such that depending on the electrical signals that you put on it, it could be a very good conductor or it could be a very good insulator. So you can switch it from conducting to insulating and with an electrical signal. And then if you think of zeros and one, kind of conducting as a 1, insulating as a 0, all of a sudden you can start thinking of little switches, little zeros and ones, and then all of a sudden you're doing math and you've got a microcontroller like the most excellent Arduino. Okay. A little bit more that most digital electronics are built in silicon. The semiconducting material that you use is silicon. This is a silicon wafer, and I can put the wafer here for you to look at. And you can see on the surface of this silicon wafer, it is covered with tiny computer chips. And so this thing has been manufactured hundreds of computer chips at a time. You could think of this as maybe 600 Arduinos. It's not an Arduino, but it kind of be equivalent. 600 microcontrollers. The next step would be to come in and a machine slices this wafer into individual chips, each one being, let's say, a microcontroller. And then if you think of something like the Arduino, and right here you've got this dual inline package or this package chip. If you could pop the lid off of it, you would see that there's a tiny chip inside of here, which was a slice off of a silicon wafer. Okay, so that means that just about everything in the world of electronics is based on semiconductors, including LEDs. But if I'm going to explain to you how an LED works, I need to go in and explain how a semiconductor works. This is the way that you can think about a semiconductor. You have to think of, let's say, something maybe in physics that you have. If you've had any physics or chemistry and you have an atom, you know that that atom has certain energy levels that an electron can be at, and they're discrete levels. It would be like if this is energy and you have an atom, you could have an electron here, an electron here, or an electron here. Say the electron can't be at any energy level, it can only be at certain specific energy levels. Well, a semiconductor is a crystal material. And a crystal material, basically the atoms come in and they're like in a perfect lattice, okay? They're not in there in random orientation, okay? The crystals line, or the atoms line up perfectly in a crystal, and then that unit cell is repeated over and over and over. As we have these individual atoms, and as we bring them together to form a crystal, because of something called the Pauli exclusion principle, these discrete energy levels from adjacent atoms begin to smear, and what we end up with is instead of discrete energy levels, we end up with allowed bands. And so this entire band of energy is allowed, and this entire band of energy levels is allowed. So this from here to here is allowed, and from here to here is allowed, and nothing between here and here is allowed. And so between here and here, this is called the band gap, or the forbidden region. So you could have an electron anywhere in here, or you could have an electron anywhere in here. These are the allowed bands in a crystalline material. All right, so now let's start talking about this semiconductor business, or about the conduction. Now I want you to think, in a lot of these things, you can kind of think of an electron as a marble. And if you put a marble in a bowl, where is the marble going to want to go? It's going to want to go to the lowest energy level. When you have an electron in a semiconductor material, where is it going to want to go? It's going to want to go to the lowest energy levels. Where are the lowest energy levels? They are down here in this band, which we call the valence band, okay? And so all your electrons end up in this valence band. And so let's draw them like this, okay? All these are here. And then this band, which is called the conduction band, okay. The conduction band is all empty, all the electrons are down here. So now, if we apply a voltage, if you're thinking about marbles, applying a voltage would be like tilting this, okay? Are the marbles going to flow? Or are they not going to flow? That's like asking, are we going to have a current or are we not going to have a current? So if I have this semiconductor material and I apply a voltage, am I going to get any current flow? Well, the first thing, let's think about the conduction band. Think of it as a tube. The tube is empty, void of marbles, no marbles. I tilt that tube, do I get marbles moving? No, there's no marbles. Therefore, there's no conduction. There's no conduction because there's no electrons here. But you say, wait a minute, there's a bunch of electrons down here. True, there's a bunch of electrons down here, but now let's think of a second tube. So this one tube is empty. Now we have this other tube. This other tube is completely full of marbles. If I tilt that tube, do the marbles move? No, it's full. So when I'm in this state, which is an intrinsic semiconductor, I get virtually no current flow at all because this one's completely empty, this one is completely full, no current flow. But now, let's think of some way that we might get an electron from here up to here. Well, let's say that I start bringing some temperature into this system. I start increasing the temperature. What's going to happen if I increase the temperature? I'm pouring more energy into this system, and I'm going to get a lucky electron that is going to absorb that thermal energy, and he's going to hop across the band gap or the forbidden region, and he's going to end up here. Okay, now I'm going to make a little better picture here because there's something more specific when that happens. Okay, so again, I'm going to have we'll just call it the valence band, and then I'm going to have the conduction band, and then I have all of these electrons down here. Okay, and now I apply some thermal energy and I get this one lucky electron that jumps up here. Now, if you think of this second tube of marbles down here, when that electron jumps up, when that marble jumps up, what am I left with? I am left with a hole here. That is where that electron used to be. Now, let's think about this. We're going to apply a voltage, and that is going to be like tilting the semiconductor. So what is this electron going to do? It is going to roll downhill. And so I am now going to get conduction from this electron that's in the conduction band. Like one marble in the top tube, I tilt it, that marble is going to roll downhill. Now, what's going to happen down here when I tilt it? Well, really what happens is this electron's going to move here, this electron's going to move here, this electron's going to move here, this electron's going to move here. So I am going to get conduction in the valence band too. So not only am I getting conduction from the electron, I'm getting conduction down here. Now you could go in and think about where every single electron moves, but what would be easier? Think of this as a whole and think about the whole moving. Okay, and this works perfectly well mathematically and physically. Rather than thinking of all the electrons, think about the whole. The only difference is electrons roll downhill and holes roll uphill. Think about like a level. Have you ever used a level? It's a tube with water in it and there's a little bubble. Okay, when you tilt it, the bubble goes uphill. But as you're tilting it and watching the bubble move, you're not thinking about the water moving, you're just thinking about the bubble moving. Exactly the same thing with semiconductors. If you have an electron go from the valence band to the conduction band, I've got one charge here that can conduct electricity, and then I've got one charge here that can conduct electricity. So it's like I've got two particles that are conducting electricity. A negatively charged electron, and this hole is missing an electron, so you could think of this as a positive charge. So the way to think of it is a hole has a positive charge, an electron has a negative charge. A hole can conduct electricity, an electron can conduct electricity. Okay, so this was the case of an intrinsic semiconductor where the valence band is full, the conduction band is empty. The only current that flows is from these lucky thermally generated carriers. Now, the higher the temperature, the more lucky electrons that you're going to get, leaving behind the lucky holes, the more electron hole pairs you're going to get. So as you increase the temperature, the conductivity of a semiconductor goes up. It increases because you've got more carriers to conduct electricity. But now let's think. That is generating a crystal material, a semiconductor with no impurities. Valence band is full, conduction band is empty. What if we put some very specially designed, very carefully placed impurity atoms in this crystal? Okay, so again, I'll draw the band gap like we did before. This is the what? This is the valence band. This is the conduction band. But instead of just using silicon atoms or whatever atom that I'm building the crystal from, I'm going to put in a very minute, tiny amount of impurity atoms. And for this first type of impurity atom, it's going to be an atom that has an extra electron about at the energy level of the conduction band. So I'm going to put these impurity atoms in, and I can do this with my manufacturing facility. These have an extra electron, and now it's very easy for that impurity atom to donate. It is a donor atom. And what does the donor atom do? The donor impurity donates an electron to the conduction band. Okay, so now these four donor atoms, these impurity atoms, donate an electron to the conduction band. So now my tube up here, it's not empty. It has four marbles. As I tilt it, those electrons move, those marbles roll downhill, and I've got electricity flowing. All of a sudden, this acts like a conductor. Okay, now what's going on in the valence band? The thing that you have to see in the valence band, though, is it remains full of electrons. Why? Because the electrons did not come from the valence band, they came from the donor atoms. So this donor type semiconductor, it is called N-type. N-type. NType. It's called N-type because N represents an electron, and so your conduction is happening by electrons, so we call it N-type. You don't have any hole conduction because there are no holes. The valence band remains full. Okay, so this is an N-type semiconductor. Well, just like with an N-type semiconductor, there is a different type of semiconductor. Again, we could imagine this being silicon atoms. This is the band gap, this is the valence band, this is the conduction band. This time we are going to put impurity atoms, but these impurity atoms, instead of having an extra electron, they have a missing electron, and that missing electron is at an energy level very close to the valence band. And so what is going to happen? This impurity is going to accept, so it's called an acceptor type impurity. It is going to accept one of the electrons Okay, so for each acceptor atom, it is going to accept an electron from the valence band. When it grabs and in effect steals that electron from the valence band, what is left behind? Holes. Okay, what do we have in the conduction band? We have no electrons up here because these electrons were grabbed by these acceptor impurities, and it leaves holes behind. Now, as we tilt the semiconductor by applying a voltage, what happens? These holes roll where? Holes roll uphill, electrons roll downhill. So now we have conduction not by electrons but by holes, and so this is called p-type. P-type, the conduction happens by hole movement, which we get by putting acceptor impurities in the crystals. If we put donor impurities in the crystals, we get some electrons in the conduction band. It is N-type conduction versus p-type conduction. Okay, so now we have two types. We've got three types of semiconductors. We have intrinsic, which have no impurities. Valence band is full, conduction band is empty. No current flow except just the random lucky ones that are thermally generated. We can have N-type material where we put donor atoms and we end up with electrons. We can put acceptor atoms, which creates p-type material, which then gets hole conduction. What on earth does this have to do with a diode? Okay, I am going to try to show you now how this leads to an LED. All right, now this is where things get interesting. What if I bring an N-type material? I'll kind of try to show you a picture here. What if I have a P-type material and I bring it next to an N-type material? A P-type material next to an N-type material. Now, it's not two separate things that I press together and glue it together. It's just as I manufacture it, I have this piece of semiconductor material and I put donor atoms over here and I put acceptor atoms over here. Then what happens? Okay, I think I will draw it like this. We will say that here I put N-type material, which means these are donor impurities, and then over here I put acceptor type impurities, so P, and so I can have a wire, and I can have a wire, and I have N-type material here, donors, P-type material here, acceptors. Now let's look at the energy bands, and let's see what the energy bands are going to look like. Well, what happens when you do that is you get this strange thing that happens, that you get this offset in the bands. Okay, this is P-type material, this is N-type material. So since this is N-type material, what do you have going on? If we go back and look at the earlier pictures, we have some electrons up here in the conduction band. Okay, and then the P-type material, what do we have? We have some holes in the valence band. Okay, so I have electrons here, I have holes here. But now, If I'm just sitting here, is there any current flowing? No, because these electrons can't get up over this hump. It's like a wall, right? The electrons want to run downhill, so the electrons stay here. The holes want to run uphill, so the holes stay here. And so I have electrons in the N-type region, I have holes in the P-type region, and absolutely nothing happens. Okay, now, what if I apply a voltage? Well, if I apply a voltage, let's say that I put a positive voltage on the P side and a negative voltage on the N side. What this positive thing does is it pulls this down. It pulls this down. And so what I end up with is something like this. You see, this step becomes much less. Now I still have electrons here, and I still have holes here, but has the wall become higher or lower? It's become lower because I've applied this voltage. Okay, so like imagine me and I can jump. If you go outside and you have a 6-foot, if you have a 6-foot fence, like this is 6 foot, I cannot jump it. But if you pull that fence down and make it 3 feet, I can jump it. And so what happens when I put this positive voltage here? This electron, some of these electrons can make it up here, and some of these holes can make it here. Okay, so now I've got a few electrons here. I have a few holes here. These are the holes that jump that barrier. These are the electrons that jump that barrier. Now you've got a hole, you've got an electron over a hole. Okay, remember in our tube, I've got a few electrons up here. I have a few bubbles down here. What can happen? That marble can go down into that hole. This electron can come here, and it's like when an electron and a hole come together, they annihilate each other, because now this becomes an electron, which is sort of what you would have here, you know, a full valence band in this p-type material. So this is called electron hole pair recombination. You have an electron and a hole recombine. Well, this electron was at a high energy level, and now it pops down to a low energy level. That energy has to go somewhere, right? You cannot produce energy, you cannot consume energy, you can only transition it. So what happens to the energy as this electron and hole recombine? It is emitted as a photon. So, how do you get light out of an LED? You forward bias it to reduce this barrier, and then you have electrons coming into the p-type region, you have holes coming into the n-type region, and you have them begin to start recombining. Okay, they start electron-hole pair, EHP, electron-hole pair recombination, and each one of these that occurs, you emit a photon. Well, if you want it to be brighter, what do you want to do? You want to lower the barrier further, so you're ending up with more electrons here and more holes here. You get more recombination, you get more photons. It is brighter. Okay, that is how an LED works. But now let's think, what happens if you put a negative voltage? So instead of this, what happens if I put the voltage on backwards? If I put the voltage on backwards, instead of lowering the energy barrier, I increase the energy barrier because I hooked it up backwards. Okay, so now this negative is moving this side up and this positive is moving this side down. Now, remember this was N-type, so we have all of these electrons. None of them are going to be able to come up here. I have all these holes, none of them. So instead of making the fence from 6 foot to 3 feet, I took the fence and I went from 6 feet to 12 feet. There is no way I'm going to jump over that. So there is no current at all, and there's no light emitted. So this kind of helps you see one of the real fundamentals of a diode, a light emitting diode. It only works in one direction. As you apply a voltage in the correctly biased way, where you put the positive voltage on the p-type material, you lower the barrier, you get electrons and holes going into the other regions. They recombine. You see current flow and you see light emitted. If you hook it up backwards, you made the barrier larger, you will get no current flow, you will get no light emitted. And that is why when you have a diode, okay, when you have a diode, you have to hook it up correctly, right? The positive has to go to the p-type material, and the negative has to go to the n-type material. And then you will get this magic happening. You will get current flowing and you will get light emitting. So one of the characteristics that's very important of a diode, you've got to put it in the circuit correctly. And this is the key of the kind of takeaway here for hooking up a diode. There's a long leg and a short leg. The long leg goes to the p-type material. The short leg goes to the n-type material. The long leg always has to be hooked towards the voltage, towards the positive voltage, okay? And that will mean that it is connected correctly. Long leg is the p-type, short leg is the n-type material. All right, now there's one more thing that we need to look at that's important. If I just look at the current in the diode as a function of the voltage. Let's go back and look at some of these magical charts that we put together. Okay, let's see. This was the one where we applied a positive voltage. We lowered the barrier. Well, the thing is, this lowering of the barrier, the amount of electrons or holes that can make it over the barrier is exponentially related to the barrier. And so what that means is when you start moving that barrier, you get exponential increase in these electrons and holes moving, which means that you get exponential changes in current. And so if I look at voltage versus current, like for a resistor, right, it's very linear that as you increase voltage, you increase current, very nice in a very controlled way. Diode not. That in the reverse direction, if you have a negative voltage, there is in effect no current at all that flows, just a tiny amount of leakage current, but you don't get any real current flow. And then as you start positively biasing it, lowering this barrier, you get a very quick and rapid exponential increase in current. What this means is that if you just come in and do something like this, and you hook a diode like this, what's going to happen is you apply that voltage, you're going to get a very large current. As you start getting that current, you very well could start heating this diode up, and then that's going to lead to even more carriers, and the thing is just going to run away and it's going to burn out. So you never hook a voltage directly across a diode because it's too unstable, that you can end up with a runaway condition, and then you will let the smoke out. Okay. If you let the smoke out of the diode, burn it up in effect, it'll never work. And once you let the smoke out, you can never get the smoke back in. And so the diode is going to be burned out. So you never hook a diode up like this. You always put a current limiting resistor in series. Okay. So this is the circuit that you want to do because of this instability. You want to put a diode, and you can do a lot of calculations, but usually a 330 ohm resistor, maybe a 200 ohm resistor, that will limit the number of current, but the amount of current that can flow, because this is a fixed resistor, and therefore you will never burn out your LED. Okay, ladies and gentlemen, That is how an LED works. You have a p-type semiconductor, n-type semiconductor. You have this barrier. By applying a voltage, you lower the barrier, you end up with electrons in the p-type material, you end up with holes in the n-type material. Electron holes combine, and then that will generate a photon. Okay, now let me ask you, what color does the LED generate? Because we have different colors, right? What color does the LED generate? Well, let's look at this electron and this hole, and they recombine and they emit this photon, and the photon is like a packet of energy. They emit this photon. What is the energy of the photon? Well, it is exactly this energy gap. Okay, you have this energy gap. That is how far the electron fell, and therefore that is the energy of the photon. That is the energy of the photon. Now, the energy of the light, we know that energy is related to frequency, that the energy of this photon is this Eg, so we have the energy of the photon is equal to the energy gap here, and then that is equal to h times the frequency, and h is Planck's constant. We're not going to worry about that, but you can just see the larger this band gap of the material that you're working with is, the higher the frequency. And then we also know that frequency is 1 over wavelength of the light. And so you can see the higher the frequency, the lower the wavelength is going to be. So if we look at frequency, as frequency goes up, you start going towards like purple and violet and then ultraviolet. Okay, the very high frequency colors, which are the short wavelength colors. If you have the frequency coming down, you start going towards red, and then you go into infrared, which you cannot see. And these are the low frequency colors and the long wavelength colors. So what color do you get out of an LED? It is a fundamental property of the material that you're using, the semiconductor material. It is defined by the band gap. And so if you want a certain color, you have to create a material, a crystal that has a certain band gap, because it is this band gap that determines the energy of the photon, which determines the frequency of the photon. Okay, this has been a great lesson. Man, put your comments down below. Ask some questions. Let's start talking about it. What are we trying to do? We are trying to look under the hood and understand how semiconductors work and understand how this darn blinking thing is working. How is it working? I'm applying a voltage. The voltage lowers that step between the two types of materials. Electrons, holes are injected, they recombine, and boom, photons come out. Okay, guys, if you like this video, think about giving us a thumbs up. Be sure and order your eLego kit from the link below so that you can follow along with the rest of the videos. Next video, we're actually going to take our marvelous little LEDs and we are going to start hooking them up and programming them. But as we do it this time, you're going to understand the physics behind these things actually work. Think about giving us a thumbs up. Think about sharing this with your friends. Paul McWhorter, toptechboy.com. I will talk to you guys later.